Hello guys, welcome to today's lecture, and today we will be talking about entity authentication. Previously we have seen message authentication. And what's the difference between the two types of authentication? Message authentication basically means that the message is coming from a particular source as claimed. So it is more like a data origin authentication, and for this the other party who generated the message may not be online to prove that the message is from that party. So it's more of an offline activity, and the message has got a few additional things with it that proves that it is coming from the claimant itself. But entity authentication here, the claimant has to prove that he or she is the person who is doing the talking. Message authentication does not happen in the real time, but entity authentication does happen in the real time. Message authentication authenticates the message, but entity authentication authenticates the entity or the party who is communicating the message. The example here I could give of is if you're chatting to some other person, that means that you have to identify that you are chatting with the same person or some other person who is masquerading as the intended person, right? So entity is more like an online activity, and the message authentication is an offline activity. There are three verification categories. So as we had verification in case of message authentication, the same kind of verification will be done here also. But the thing is, here there will be a claimant that claims that I am Alice, and the verifier will verify whether you know a secret that Alice is supposed to know, whether you know something that verifies that you are an Alice. And those some things are actually divided into three categories. There's something that is known to you. Do you know a certain secret? If you provide me with that secret, I would identify that you are the very person. For example, if you know a PIN or a password. So when you log into your Gmail, your Facebook, any account, what do? You provide your username and a password. Password is that secret that only you are supposed to know, right? So something known is one of the categories. The other categories is something possessed. That means you have got your identity cards. If you take the example of the ATM, then you have got your debit cards or the credit cards. So these are the cards that are unique to you, and when you insert them in the machine, then only machine works. And then something that you inherit. Now these include your biometrics, your handwritings, like biometrics includes your fingerprints, your retina scan, your iris scan, and facial recognitions, and all such things that actually belong to you. You do not have a control over it, but that is unique to you. Your DNA is unique to you. So these things are verifying the identity of a person. If we talk about the passwords, there are two parties who are communicating. One is Alice, the other one is Bob. Alice is the claimant, and the Bob is the person who has to verify that, okay, am I talking to Alice or somebody else? So Alice will send the username and the password, that I'm Alice and this is my password. When password reaches the Bob, Bob has to have a table that has the entry of the Alice and the corresponding passwords. So here you can think of a Facebook server and yourself. So you are Alice over here. The Bob is the server of the Facebook. When you provide your credentials like username and password, that server looks into the database, looks into the table, and selects out the password with respect to your username, and then it matches. If the two values match or not, means the value that is written in the database matches with the value that you have provided. If they are same, then you grant access, otherwise you deny the access. Now there are various possible attacks onto it, like eavesdropping. Somebody could drop into the line and listen to the communication. Somebody can steal the passwords, accessing a password file, and guessing is more like a brute force attack over here. So I'm not talking about the eavesdropping. We have already seen stealing a password. Somebody is trying to recover your passwords from the encryption messages that are passing on, or the type of communication, or timing attacks, whatever. So stealing a password has got different mechanisms. Then guessing a password is pure brute force. That also depends on the kind of algorithm that you are using. Such attacks are dependent on the algorithm. So let's not talk about it. Let's not talk about the network security right now. Let's not talk about that when this is passing through the insecure channel, somebody is able to hear it. We are assuming that we have seen enough lectures regarding the same. If you want confidentiality as a service, we can have that. We can have message integrity as a service, authentication as a service. So we can have those services, and we are assuming that no attack has been taking place over here. But what we are more concerned about is our database right now. in this lecture, that in what format should I be saving the information? Because if what if somebody gets an access to the database or the table, that is the third kind, accessing a password file, what happens then? If you are saving the passwords in clear text into the files, then just by having an access to this table or this file, a person will have a list of usernames and a list of passwords corresponding to it. So everything would be compromised. So you need to have a mechanism in which you are not only saving the passwords, but you are somehow maintaining the secrecy of those passwords as well if the file is compromised, right? So here we are dealing with the attacks on the database where the file is getting compromised. Then how to save your passwords from that? Okay. So this is your simplest scheme, which is not worthy at all, because compromising a file will lead to the exposure of all the passwords. So the second scheme here is that instead of using saving the passwords directly, you save the hash of those passwords, and you know that hash are the one-way functions. One-way functions means that you cannot create the password from the digest that has been created using the hash function. So you cannot reverse back. If now your file is getting compromised, then you cannot pretty much get to the password. So password is now secret, but you have an access to the hash, which doesn't make any sense, because whenever you are providing with your value, that value would be hashed, and the value from the database and the hash value that has been generated would be verified. Now, if by looking at the database you are not able to get the password, that means it's very unlikely that you would be, as an intruder, be able to provide the password pass that gets to the hash value that is given in the table, right? So you are much secure now, and the job of this rhombus box is to match the two values, and if the values are same, then you grant the access, otherwise you cannot. Now the attack over here is dictionary attack. In dictionary attack, you already compute a dictionary. You already compute the hash values of the commonly occurring words or passwords. For example, a person can frequently use a password like 12345. So they will have an entry for 12345 with the corresponding hash value. They will make an statistical analysis that what are the frequently used passwords by the people, and they will have the corresponding hash tables already generated in the table, right? And that table will be called as the dictionary. So this is a dictionary attack. Sometimes it is also called as a rainbow attack, but there is a slight difference from the dictionary attack, but the essence is the same, right? Other thing is, if I tell somebody that there is a particular website that takes in only numerical passwords and the limit is 6 digits only. So that pretty much means that there are values from 0000000 to 9999999. There are only 10 lakh values, and for those 10 lakh values you can generate the hash of every number from 0000000 to 999999, and you can have a dictionary formed of the numbers that you have generated and the hash values. Now all you have to do is you have to match the hash value from that dictionary to the hash values that are written over here. If there is a match in the hash values, that means the corresponding number written in your dictionary is actually the password. So the password can get compromised if your password scheme is not very secure, if it is using simple numbers or simple alphabets, if it is not a mix of capital and small and special characters, then there is a problem that dictionary attack may happen. So in order to avoid this dictionary attack, what we want is that whatever password I generate, if I add certain bits to it, then not only the size of my password increases, but also a random string is getting attached to it, right? And that random string is pretty much creating a different hash value altogether. So in the third scheme, we will try to have a salt added to the password. So salt means a random string added to the password. So this random string is represented by SA. So if I have got a password like hello world 123, and the salt value is a random string of such a kind, so these two will be forming as the input, and these two, the concatenation of these two. Now salt value could be added before the password or after the password, that depends. In my example, I'm adding it after the password. So the strings to be hashed will be the concatenation of these two strings, and the hash value would be generated by passing it through the hash algorithm. So this is the hash value that gets stored over here, right? And now whenever Alice is trying to prove that she is Alice herself, then it provides the username and password. That password is then appended with the salt value and passed on to the hash function, and then hash function would be compared the value generated with the value that is written in the database, and if they match, it will be granting the access to the page, otherwise it will be denying the access to the page. Now the thing over here is, you may say that salt is already mentioned in the table, and if the table is getting compromised, the person will know the salt value, right? And if one knows the salt value, then that could be easily added to the password value, and you can calculate the hash. But the thing over here is, in the previous example where I was talking about the dictionary attack, I told you that in dictionary attack you have got pre-computed hash values, and you match the hash values that are written over here with the pre-computed hash values of the dictionary table. But now, since a salt has been added, you will not be having the hash values matching with the hash values of the dictionary that you have created. Now these salt values are random values, meaning that if Alice and I, Zafariab, are using same password, that is hello123, hello world123, both of us will be getting different salt values. That means we will be getting different hash values, right? If two people are using the same password, still the hash values will be different, thereby increasing the difficulty for the attacker to perform the attack. Initially, in the previous scheme, if two people had the same password without the salt values, they would be getting the same hash values. So by just comparing the hash values of the dictionary table and the hash values that are given in this table, you get to compromise the password of two different people, right? But now you won't be able to do this. In order to carry out the attack for one single person, you have to attach that salt to all the values of your dictionary, and then you have to perform the comparison of the newly generated hash values. Now when you have to repeat this cycle for every user entry of this table, it becomes a very tedious, very cumbersome task, which is not possible. Hacker can be able to still steal the passwords from this file, but the intensity of the attack is not that much, because a few more calculations have to be performed, which are not only time taking but a costly affair as well for the hacker. So it is computationally more time taking as compared to the other processes. But book is not dealing with one more, but there is a concept of pepper also. So salt and pepper technique combined will increase more randomness, and that randomness will again lead to difficulty in the calculation of the passwords. That protects you from the attack to a great extent, but it does not eliminate the chances of the attack. Attack is still possible. The third scheme is that you are combining two different identification or the verification categories. For example, we use the ATM card. So here not only you are just providing the password, but you are also having an identity card. So even if your password file is getting compromised and the person knows the PIN, but the PIN is of no use until and unless you insert a card into the machine, right? So if that card is with you, other person, even after knowing the passwords, won't be able to do anything. So in order to give you more safety and security, the two verification categories can be combined, and something of the kind of the ATM card concept could be generated, right? So the card belongs to something you possess, and PIN belongs to the something that you know, that is a secret. So this is your fourth scheme. One-time password makes salting and eavesdropping useless. So one-time password, as the concept is that every time you get a new password set of values on your SMS, and when you enter those set of values, set of digits, you pretty much get an access to the page or the service that you are looking for. So one-time password is one of the most commonly used things today, and for any two-step verification, we generally use one-time passwords. So how do these one-time password technique works? The first one is that you as a user and the system agrees upon a list of passwords before the communication starts. But that will be a long list of passwords because you will have many interactions with that system. So that long list of passwords would be difficult to handle. And the other thing is, if you both are not having the same sequence of passwords, if it is randomly distributed, then searching has to be and matching has to be performed, which is computationally taking more time. Although system needs to perform long searches, which is very infeasible. That's not a good technique at all. So we go for another technique where the user and the system agree to sequentially update the password. So you agree upon a common password at the beginning, and that password is used as a key to generate another password during your first interaction itself. So first time when you are accessing, you use the pre-computed, pre-shared password, and on your first access, you generate another password using the previous password as the key. So this way, every interaction you will be agreeing upon a new password which will be used in the subsequent access. But the problem is if intruder gets to know the initial password, the first that you had shared, then the user would be, then any intruder would be able to generate the same sequence of passwords. So it appears to be a very secure and good scheme, but the compromising of one password will lead to the compromising of all the other passwords. And the third scheme is that the user and systems are sequentially updating the passwords using the hash functions, and the hash functions are necessary over here because hash are irreversible functions. So it is similar to the previous examples that we had been taking, that there is a table and you agree upon a random n number, and that n will signify that how many hashings have been performed onto the initially shared password. And whenever Alice is submitting its username and password, it will check, okay, Alice has got the value n over here, so that n would be provided back to the Alice, and that n minus 1 times hashing would be performed onto the initial p naught, which will be sent to the Bob, and the previous table would be updated to the new values, that is n minus 1 and h to the power n minus 1. But the actual value over here will be passed onto the hash function, because applying hash onto this value will generate the value h to the power n p naught, and then it will be compared to the value that is written in the database. And if both the values are same, you will have access to the page, otherwise you will be denied access to the page. Here you will see that the value that is being shared is a very random value, because the initial password is going on, having several hashings performed over here. This scheme is also called as the Lamport ODB scheme, and this is not very commonly used. The other way to prove that you are the intended claimant is to have a challenge response mechanism where the claimant proves that claimant knows a secret, but it does not send that secret. It uses that secret. So there are two components to it, the challenge and the response. So the verifier, which is in our example Bob most of the time, will be sending a challenge. Challenge means it will be sending a certain value that could be a timestamp, that could be a random number that is generated every time an interaction or a challenge is put forward. So every time there will be a different number. And response means that the claimant will be passing that number through a specific function that proves that that function can only be performed by the claimant itself, and then it returns the result of that. That means claimant knows a secret. According to that secret, it acts upon the value, generates a result and sends back, but it is not sending the secret back. It is sending the result by applying that secret back to the Bob, and then Bob has to verify. Let's look at some of the examples. So if I'm using the symmetric key for challenge and response, the two parties are Alice and Bob. Alice says that I'm Alice to the Bob, and Bob has to verify whether the claimant is actually Alice or not. So it throws a challenge to Bob. So this random number generated by Bob is represented by RB. RB is the challenge given to the Alice. Once Alice has its challenge, Alice will encrypt it using the shared secret key, because it is symmetric key. So that there is a shared secret key KAB, which is shared by Alice and Bob. So when Alice encrypts the message with KAB and sends it back to the Bob, how do Bob verify? Bob will try to decrypt this message using the same KAB, And after decryption, when Bob gets the same RB value, that means it can only be encrypted by Alice because KAB is a shared secret between Alice and Bob, right? So no intruder will be able to guess this value of key and encrypt the message, right? So this way, Alice's identity is confirmed. Now you may argue that if this message is intercepted by the intruder and he is sending this message over and over again. So what did we say in the previous slide? We said that the challenge is a time varying value, right? So it could be a timestamp. So if RB is representing a time value, that later stage time would change. If it is representing a random number, then every time a new random number would be generated. So if somebody captures this message and starts replaying the same message over and over again to the Bob pretty much knows that this message is encrypted by Alice, no problem, because it's a random number. And once a random number has been used, it cannot be reused again. Next time it would be a new value. So replay attack is not possible under this scheme. So some other person cannot masquerade after capturing this ciphertext. This is unidirectional authentication because here only one of the parties is able to authenticate themselves to the other one. Other could be that instead of using the random number, if I use a timestamp. So timestamp, but it has, a limitation. The limitation is that the Alice and the Bob should be having a synced clock. Here, Alice will be sending the identity of itself appended with the timestamp and encrypting it with the shared secret. When it reaches Bob, Bob decrypts it using the shared secret KAB, and it gets the value of Alice and the timestamp. And looking at the timestamp, it will understand that since their clocks are synced, so the message would be coming from the Alice. Now, if you want to verify both the parties who are in the communication, then Alice would be sending its identity to the Bob, and Bob in return would be sending a challenge, that is a random value generated by Bob. Then Alice not only encrypts the value of RB, but also gives a challenge RA to the Bob, right? And encrypts it with the shared secret, a secret shared by Alice and Bob. So when it reaches the Bob, Bob decrypts it using the shared secret KAB, and it gets the value of RA and RB. From RB, it verifies that the message is coming from Alice, right? But RA is a new value, so that means RA is a challenge thrown by Alice to Bob to verify that Bob is the one to whom Alice is talking to. So in return, what Bob has to do is Bob has to encrypt the message and send it back to the Alice. The thing over here is the order of RA and RB has to be reversed, because if you are not reversing this order and if this message is captured by an intruder can replay the same message back to the Alice, right? If intruder is sending it back to the Alice, intruder will not be able to change the sequence of RA and RB because intruder does not know the shared secret of A and B, right? The sequence can only be changed by the Bob. So Bob decrypts it, gets the value of RA and RB, rearranges them into RB RA, encrypts it using the shared secret and send it back to the Alice. At Alice, when it decrypts, Alice gets the value of RA to verify that it is the challenge thrown by Alice to the Bob, and therefore the message should be coming from the Bob. From RB, it verifies that the order of the two values have been changed. These are the two values that were sent as encryption by the Alice. So Alice is pretty sure that the Bob is sending the message back because this could not have been done by any intruder. So in this way, both the parties are throwing challenges to each other and verifying their existence. So it is bidirectional authentication. If you are using the asymmetric key, then Alice says to the Bob that I'm Alice, and the Bob says, okay, if you're Alice, then Bob uses the public key of Alice to encrypt the identity of Bob and RB and sends it to the Alice. Why it encrypts with the public key of Alice? Because this can only be decrypted by the private key of Alice, and the private key is something that is private to the Alice and nobody else can know that. Therefore, if it is Alice, then only it will be able to read the value of RB, right? So at Alice, it reads the value of Bob and RB and returns back the RB. So in this way, Alice gets verified to the Bob. This is unidirectional because Alice, only one of the parties is getting verified, right? If both the parties have to verify each other, so both of them will be sending the challenges to each other. Alice now not only sends the identity but also sends the challenge to the Bob, encrypted by the public key of Bob. If Bob is able to decrypt it and send the value of RA back to Alice, that means only Bob can do this, so Bob is verified. So what Bob does is it not only decrypts the message and gets the value of Alice and RA, but it then packs a new message with its own identity, the response of the challenge thrown by the Alice, and then again it appends a random number to throw as a challenge to the Alice. If Alice is the one who she claims to be, then Alice would be able to decrypt this message and read the value of Bob, the response of the challenge that it has got, and a new challenge itself. If it is the Alice is able to read the value of RB, it should be able to reply RB back to the Bob. If this happens, then both Alice and Bob have verified each other's existence. If I'm using the digital signature, so I will be signing the document, and for the unidirectional flow, Alice would be sending the identity request to the Bob. Bob will be sending the challenge RB to the Alice, and now Alice would be signing the document by the identity of Bob and the RB. So it tells that it wants to communicate to Bob, and it also says that this RB is the challenge, the response that the Bob has thrown. Why is this Bob attached? Because in case of digital signature, we said that we not only send the signature, but we also send the message along with it. So the message encrypted by this signature is Bob and RB both, right? Bob has been supplied back to the Bob. Why? In order to tell Bob that one of the documents that are signed is Bob and the other one is RB. RB was not sent openly because RB is a challenge thrown by Bob itself. So Bob already knows the value of RB, right? What it doesn't know is that along with RB, Bob's identity has also been signed. Therefore, it tells that, okay, your identity is also signed along with the challenge that you have thrown. So when this reaches over here, signature means that you have encrypted it using the private key of Alice. Now, since this is encrypted by the private key of Alice, which is represented over here, it can be decrypted by the public key of Alice, which is known to everybody. So Bob uses the public key of Alice to decrypt this message and get the value of the Bob and RB. Now this Bob will be mapped to the message that it is getting. It will say it's a match. So verification has will be completed, and it will be comparing the value of RB to the R challenge it has sent. And when two values match, then there will be an accept. That means the identity of Alice has been verified. If you want to carry out a bidirectional authentication, then you get the challenge from the Bob. You sign the document along with the identity of Bob and send a challenge to Bob as RA. Also, when this gets decrypted at the Bob, Bob will be able to verify the value of RB that it has sent for the challenge and the identity Bob. And RA is a challenge, so it will be signing the document and sending it back to the Alice and telling the Alice that along with the RA, it has also encrypted or signed the identity of Alice, and therefore both these parties will be verifying each other. Then there is another scheme that is called as zero knowledge. In zero knowledge, the one of the protocols is Fiat-Shamir protocol, and here Bob has to verify the identity of the Alice. This scheme is based on the public key crypto system, and here you will have a value of n which is public. So n is that value which is used for the modulus calculation, mod n, and Alice will be having a secret key that is a private key S and a public key that is V and a random number R. Out of these three values, Alice knows the private key and the random number, but Alice's public key is known to the Bob as well. So Bob can only know n and V. The relationship between the V and S is also known only to the Alice, that V is equals to S square mod n. So out of all these informations, Bob knows only the value of V. That's it, nothing else. So Alice would be sending a message X, which is actually equals to R square mod n, and this will be serving as a witness to the Bob. It has been sent to the Bob that the value of X can be witness means that now this X can be utilized by the Bob for verification. Therefore, X is acting as a witness. In return, Bob gives a challenge C. The value of this C could be 0 or 1, right? So when this challenge has been given to the Alice, Alice will compute the value R into S to the power C mod n. So look over here. The value of Y has been sent as a response to the Bob, and Y calculation is involving the calculation based on the challenge that is given and based on a secret or a private key itself, which is not known to the Bob. After this interaction, what Bob knows is the value of V, that is public key. Bob knows the value of X, which is the witness, and Bob knows the value of Y, which is the response from the Alice. At the Bob's end, it has to perform two operations. It has to calculate the value of Y square, and it has to compute the value of X into V to the power C. Mathematically, if you see, Y square is equals to R into S to the power C whole square mod n. If we break it down, then we'll see R square into S square to the power C. R square is actually the value of X, so the X, and S square is actually the value of V, so V to the power C, right? So this Y square is actually equivalent to X into V to the power C. Now this red equation is telling you that the two values that the Bob is computing are same, right? So these two values are equivalent. If Bob is able to generate these two values, it will compare if they are equal. So in case of yes, the identity is verified. In case of no, it is not verified. But if you look over here, is the challenge is only the value of 0 and 1. So there is a 50% chance that any intruder can verify herself or himself. For example, if there is an intruder, this intruder does not know the value of the private key of Alice. So that is one of the limitations. Now since it doesn't know the value of the Alice, it will be modifying certain values over here. So what it does is, it assumes if the value of the challenge given by Bob is 1, so it assumes that C is equal to 1. In that case, it provides the value of witness as R square upon V and not just R square, because he is an intruder. And it provides the value of Y as R. When it does so, at the Bob's end, when Bob calculates Y square, it gets the value of R square, which is equals to X into V. Why? Because look at this equation, R square is equals to X into V, right? Since it is assuming the value of C equals to 1, the value computed by Bob would be X into V to the power 1 over here, which is there, and Y computes the value of Y square, and you will see that Y square is equals to X into V to the power 1. Therefore, Bob will be able to verify an intruder. If intruder assumes that the value of C is equals to 0, then in that case it deliberately sends the witness value as R square, and the value of Y is equals to R instead of R into S to the power C. And now when you calculate R square, then this is equals to Y square is equals to R square because of this equation, and this R square from this equation will tell me it's equals to X. So it is equals to X, and I'm writing it down as X into V to the power C because this is what Bob calculates for verification. So assuming C equals to C, the value over here will be calculated as X into V to the power 0, which is 1. So it is equivalent to X, and the value of X is actually R square that has been provided as the witness. So when you calculate Y square over here, it will actually be R square. R square will give you X. So again, Bob will be able to verify an intruder. But the thing here is, it assumes when that C is equals to 1. But what if the value of C was 0? It is predicting, the intruder is predicting, but it is not necessary that the prediction is always correct, right? Therefore, when intruder assumes C to be 1, but actually C is equals to 0, then this scheme falters. Then Bob will not be able to verify. So there is a 0.5 probability at each step that Bob would be able to verify. But imagine if this scheme of zero knowledge this protocol of Fiat Shamir is repeated 20 times, then what happens? It is highly improbable for any intruder to generate the correct values or assume the correct values all the 20 times. So the probability keeps on decreasing of getting the correct assumptions every time, and therefore intruder will not be able to guess correctly all the 20 times when this challenge is repeated. But if the person is Alice, it doesn't have to do anything. Every time Alice will be able to prove herself, right? Therefore, because this is a simple scheme has got a slight shortcoming, so the challenge should be thrown not just one time but multiple times in order to verify that the other party is Alice and not any intruder. आप एक बार में इसको डिसाइड नहीं कर सकते. Then comes your biometrics, and biometrics is something that you inherit. So it includes the features that cannot be guessed, stolen, and shared, and they are personal to you. It has got various components like the input sensors, readers that captures the information from your body by scanning and other things, and then you need processors and the storage devices where you keep those data into the databases, and later on when the same person goes for verification and authentication, that then you provide those inputs to the machine. Again, you need an input device that captures a processor that goes back to the database, checks for the values, and then returns back whether to accept you or reject your identity. So that it involves various components. Then you have got a process called as enrollment, which means that for once you have to go to provide your credentials. For example, when you go for the Aadhaar card, you initially went there and they scanned your iris and they scanned your fingerprints and everything and made a database out of it. So that was the process of enrollment. You got enrolled, and now when you go for any services, they authenticate you. So authentication is basically two kinds: the verification and identification. Verification is when you have to verify explicitly one person. For example, I say that okay, I have signed a document, and you have to verify whether I have made the correct signature or not. So you go and one on one match my current signature to the signature that is present in the database, and then you can come out and you are like, okay, oh, this is a valid sign or a not a valid sign. But in case of identification, it is like you are giving access to a person into a building, and there is a authentication system placed at the entrance itself. You go over there, you place your fingerprints or your iris is scanned, and then it is checked with the complete database of the authorized personnel. And once it gets verified from one to many matching, you get an access into the building or unauthorized zone, right? So verification is one-to-one mapping, and identification is one-to-many matching, right? So that's a slight difference between the two. If we go for the biometric techniques, then the first one is your fingerprint, and fingerprint, as you know, is unique for everybody, and this fingerprint is used for verification and identification, both the services. It is basically conducted in two ways, that is minutia based and image based. In image based, what happens is that your fingerprint is stored as an image into the database, and whenever you go for authentication or verification, you provide your fingerprint, a new image is captured, that image is compared to the images in the database. If there is a similarity, then you are allowed access. The first approach that is mentioned over here is a minutia based, which means that graphs will be plotted in order to give the informations of the individual ridges, start and stop, and the branching of the ridges. Ridges are these small lines that you see in your fingertips. In iris, your iris pattern is considered to be unique, and that is scanned and saved as an image. And later on, when you go for a verification of an identification, it will be scanned again, mapped with the database at the back end. Iris is one of the very accurate measures because it tends to be stable over a person's life. In face recognition, you analyze the geometry of the face, you analyze the distance between the various facial features such as nose, mouth, and eyes, and the accuracy is good, but it varies with the age. If you have grown facial beards, then the accuracy won't be great. If you have wearing the eyeglasses and your enrollment was without the glasses, then there will be difference. As your age progresses, there will be a different slight changes in your facial features, and thereby affecting the accuracy of the face recognition. But still, this approach is used for verification and identification both. Then you've got your hands, and the uh, hands images are stored in a way that they try to find the measures of the dimensions of your hand, the shape, the length of the fingers, etc. In voice, they measure the pitch, cadence, and tone in the voice. Accuracy is good, but it affects with your age and illness. And DNA is the most stable thing, extremely accurate. It is having a certain pattern during your lifetime and even after your death as well. DNA is basically a chemical that is found in your nucleus, and it gives you the most accurate results.